Hello everyone, I'm Tony Lyons and welcome back to the CG Compositing series. Today we're going to be continuing on with material AOVs and talking about refractions and reflections. So if you remember from this graphic that I had about the simple and intermediate and complex ways to separate the material AOVs, which we have gone over in previous videos, so if you haven't seen those, go and check those out. But always in the bottom there was emission, which stayed the same. Basically, it doesn't get broken down further. And then kind of as an exception with this little asterisk, we have refractions and reflections. And I'm going to be honest, I've been putting this off for a long time because it's a bit confusing and hard to explain and wrap your head around. But there is kind of an initial problem that we have when we're dealing with refractions and reflections. So basically, refraction and reflection passes contain all of the other passes in it. Basically, it refracts or reflects the beauty render. In other words, objects in the refraction or reflection passes look like the beauty render and cannot be broken down into these further steps, at least not out of the box or by default, which can cause a problem in compositing. And you can see in this other graphic where I have the big boxes of diffuse, specular, and emission, and the different levels of complexity, we had to put the reflections and the refractions in this others and exceptions simple category. And it's other or exception because basically it is the beauty render that you're seeing in a reflection or a refraction. So this render is made by Adrian Puello using Houdini and Solaris. So thank you, Adrian, for providing the render for us. And we have basically a glass bowl full of these like balloons. And then we have a mirror surface that is reflecting the glass full of balloons. What we would expect is that if we broke this out into diffuse and specular, that we'd get all these little highlights and then the color of the balloons would be in the diffuse pass. But that is actually not what we get. We get this for the diffuse pass. And so you can see the table and a couple of the balls here at the top of the balloons are showing. The same thing with the indirect diffuse. So, the table is showing in some of the balls, but everything that was this glass surface or this mirror surface are showing up black. They're kind of excluded. So the direct specular pass is showing the environment reflecting in the mirror and also the environment reflected on the glass that is the bowl, but not the individual balloons or balls that are inside of this glass. But if we go back to the beauty render, we can clearly see that there are some highlights on the balloons themselves, but they don't show up in those reflections. They only show up on the balls that are not inside the glass. And then we have this coat pass, which is sort of a surface level specular, so only those balloons that are not inside the glass are showing up there. Now, if we look at the indirect specular pass, we notice that the mirror is reflecting all the objects in the scene. So the majority of what we're seeing in this render that is in the mirror is showing up in this indirect specular. And again, only the indirect specular of the glass object, the bowl that's holding the balloons, is showing up and not the actual indirect specular of the balloons themselves that are inside the glass. But there's a kind of obvious problem going on, which is that the balloons that we're seeing in this one pass have the diffuse and the speculars already there, and there's no way to separate those out at the moment in the state that it is. And so basically, this is just reflecting the beauty of everything else in the scene. And then we have this transmission pass, and transmission is a synonym for refraction. Solaris was calling it transmission, I think. But you'll see that this accounts for all of the remaining things that are inside of the glass. So just breaking it down, we have our diffuse pass, which is this, and then we have our direct specular and coat. And we're still missing everything inside of the glass bowl and everything in the mirror. So the mirror is coming in when we add our indirect specular, which is this pass, along with some other indirect speculars in the scene. And basically, all of the remaining things inside of the jar are coming in just one big pass, which is the transmission. So in other words, anything that we are seeing through the glass object is showing up in the refraction or the transmission pass. And in this particular scene, without the indirect specular or the refraction pass, we don't have too much going on. So they're pretty critical to the outcome of the rebuild. This poses a pretty obvious problem of what if I wanted to adjust the specular highlights of the balloons that are inside the glass, or what if I want to change the colors of the balloons that are inside the glass, or basically anything else that is going on through the glass. So we don't have a lot of power or control in this situation. And exactly the same thing with the indirect spec. Same problem, like how would I separate these balloons from the glass? It's basically just receiving a beauty render at this point. So in some renders, these refractions or transmission passes might not be so obviously problematic. In this example, we have the diffuse pass, and we seem to be missing some objects, and some of them are other lights, which are in the emission pass, but we're also suspiciously missing the clock and things outside of these little glass windows. And it might just seem kind of unusual, like you go to this transmission section, refraction. So you might say, okay, that's a bit strange that they're over there, and but they look like diffuse. So you might just think, we'll just add those to the diffuse pass. And in this case, it's not that problematic because it kind of makes sense to go with the diffuse. And even though there's a little bit of specular highlights there, you're not really missing out on too much adjustment there. So in other renders, it might be a little bit more problematic, like this one, where if we start looking into the passes, we're not getting the information everywhere. So here's the diffuse pass, and we're missing, for example, this scale and some of these light bulbs. And if we go look at the spec, we get some, specular from the glass exterior, but we're still not seeing the details of the things seen through the glass. And those are being captured seemingly by this transmission pass or this refraction pass. And we're getting all sorts of objects in here, like these glass and this, which seems like almost a diffuse pass, but it's just things that are, being seen through the glass. And in this case, some of the light is passing through the hair, so that also shows up in the transmission pass. But we can't really break this pass down any further. I mean, at the very smallest level, it is just this kind of beauty pass. So, for example, if we look at the texture albedo pass here from the diffuse, we can't adjust anything, for example, in this scale. So if I wanted to go change the color of this scale, normally maybe you'd go to the albedo and change the texture, but you can't do that anymore because what you see is what you get. So yeah, it can be a little bit problematic, and we're limited to how much we can adjust these passes. We actually end up rendering reflections quite often, and that's because when we composite objects into the scenes, those objects usually contain reflections in the environment that we need to also comp in the reflection. And if we take this example here, where I have like an armored mech that I rendered in Blender, we have just like a ground plane reflection, which is really common to do for objects that you're integrating into a live action plate. And if we look for that reflection, it doesn't really show up anywhere except for that indirect specular pass. So it is only showing up in that indirect specular pass. So you could imagine if I went and changed all the colors of the mech, that I would not be able to do the same thing for this one pass, because this one pass is just a beauty render, basically. There's some common terminology when talking about refraction that can be a little bit confusing because the words sound very similar. So let's take a moment to break down what each of these terms mean, being transparency, transmission, refraction, and translucency. So we'll just step by step go through them and explain what they're referring to. What is transparency? We'll start with the most basic one to explain. Transparency is the ability to see through an object or surface onto what's behind it. So in this case, it's as if the object or material is completely ignored or non-existent and does not have to do with how the light is interacting with the material at all. The light that is passing through this transparent object is not distorted, which is refracted, nor does it scatter or change color, which could be the case with translucency or transmission. And transparency basically only has one setting, which is amount, or how much can I see through this. This is working exactly like an alpha channel in compositing, so you can imagine a black and white matte, and wherever is black, you're seeing right through it, and the light is not really interacting with anything, it's just pretending it's not actually there. So what is transmission? Transmission is the passing of light completely through a material. You can see this little graphic here. The light is passing through the material, and we see it from the other side. Refractive, transparent, and translucent materials all transmit light, but opaque materials do not. If light is not transmitted through a material, it may have been reflected, which is the specular, or absorbed. Transmission can sometimes cause the light to inherit a color tint as it passes through and interacts with the material. Think of colored liquids or tinted glass, for example. And this is a setting in 3D. If you set the color, the light passing through that material will inherit that color. What is refraction? Refraction is the change in direction and speed of a light ray as it travels through or transmits through different mediums. For example, from air to glass or water or plastic. So when light is entering and changing into these different materials, it changes direction. The two most important characteristics of refraction are, number one, the light passes through the material, and number two, the light changes direction. The amount of distortion, bending, or change in direction of a light's path while passing through the material depends on factors like thickness of the material, angle of view, and the material's index of refraction. Basically, the shape of the object, the angle in which the light is entering, and the type of material are all going to be having factors in how much that light is bending and changing directions. These images are all showing different shapes and angles of these glasses of water. You can see here that we're seeing the background of this window pane through the glasses, so it would be here, and this is corresponding with this shadow here. So that's what's being refracted, but looking at it from a different glass and a different angle, it's showing up in a different spot, and in all these glasses, it's kind of showing up in different areas, perhaps. So yeah, depending on the shape and the angle of the glass, it is showing us different distortions of the background. Another example is here, where even though all the glasses of water are filled the same way, because we're looking at slightly different angles, it is refracting the background in different ways, and we're seeing a different kind of result of that refraction. Okay, so let's clarify the difference between refraction and transmission when it comes to our CG passes, and why these renderers are sort of having a battle of naming between these things. So transmission is only referring to light that is passing through an object. That's pretty much the only requirement of transmission. Refraction is requiring the light to have changed direction and pass through it. So oftentimes the render pass is showing both of those things happening at once. So some render engines decided to call the pass transmission because it's referring to light passing through their material. Other renderers call the pass refraction, referring to the change of direction, bending, or distortion of the light. Both terms in this case are referring to the same phenomena, just focusing on different aspects of the light's behavior. Transmission might even be a more accurate label because technically a material could have a refraction index of 1.0, which is a setting that you could change in the material, meaning that no refraction or distortion is actually occurring, but the light is still transmitting through the object. In other words, all refractions require transmission, but not all transmissions require refractions. Why is light redirected during refraction? It turns out light travels through different mediums at different speeds, depending on the density and makeup of that medium. And examples of mediums would be a vacuum, which is, space, air, glass, plastic, water, gases, basically anything that you can see through in real life, right? So all of those things, the speed on which the light is going through that is actually changing. The change of the light's speed while passing from the first medium into the next causes the light to change direction when entering into that second medium. Remember that light is a wave, okay? It's not a straight line. It's actually moving back and forth in a sine-like pattern. Considering that light is a wave, we can almost imagine that it has a certain thickness to it. And when it hits the surface, when it hits a new medium, one side of that wave could slow down first, which would end up turning or redirecting or bending the light towards a new direction. Just imagine a car going down a road and one of the tires hits sand before the other tire hits. So one of the tires would slow down and turn the direction of that car. It's basically the same thing that is happening here. And it's actually why the angle of where the light is hitting it is very important, because the harsher the angle that it hits, the light will end up turning more. And here are some excellent graphics trying to describe this phenomenon where the light wave is hitting and one side of that wave is speeding up or slowing down before the rest of the wave and causing it to kind of turn just because it is not happening all at once, right? Color light wave frequencies. Remember that different frequencies of the light spectrum show up as different colors. So some of the higher frequencies show up as blues and purples, and some of the lower frequencies as yellows and reds. Color spectrum refraction. So even these different frequencies of light, the colors, refract at slightly different angles, and that causes the colors to separate. And this is exactly what happens with colored prisms. So these different frequencies bend at just a little tiny difference, but when you spread that out over a distance, they start to separate out more and more. Violet being the most refracted or having the most change in direction, and red being the least refracted. A combination of this refraction, color separation, and reflections within the water droplets allows us to see rainbows. I never really knew how a rainbow worked. I knew it was light passing through water droplets, but I thought this was such a cool understanding of, because of the different frequencies changing in different directions, and we're seeing it at a distance, that we end up seeing those colors shifting, and that's what we're seeing the rainbow being caused by. Let's talk about index of refraction. Different materials have different densities and makeups, and that will cause light waves to move through at different speeds, as we mentioned before. This is measured scientifically with an index of refraction, which measures how fast light moves through that medium, and therefore how much it will refract. An index of 1 is the light's speed in a vacuum, or no change in direction at all. And higher numbers mean light travels through that medium slower and the light will bend more. We can see here a table of different materials and the refractive indexes, and then kind of an illustration. So for example, water has an index of 1.33, while glass has 1.52, meaning that light bends more in glass than it does in water. Lighters are actually entering this refractive index into their materials and looking them up and making sure that they have the right index of refraction, so that the light that is bending in the CG render looks accurate to how it would look in real life. In CG, this index of refraction is an attribute setting on the materials that will make it more or less refractive. So we can see here, this is a very, very small level of refraction, so the background is barely bending at all. And then we increase it more and more, and we get more bent light, and the background looks even more distorted. Refraction re-entering the original medium. When light goes from a fast medium to a slower medium, and then back into that faster medium on the other side, it has another refraction turn. This time, instead of one side of the light wavelength slowing first, one side speeds up first. If the exit angle is the same as the entrance angle, it will reverse the light wave back to the original direction. And this exiting light ray is parallel to the original light ray direction, it's just offset because of the time that it spent inside of the material. These illustrations are trying to show that effect, and if we take the middle one, so light is passing through air, and then it's hitting this plastic material, I think it's plastic, and while it's inside, it's changed direction, right? That's the first change. And it goes through, and while it exits the other side back into air, it continues on. So the exiting light ray is actually parallel to the original light ray. It's just offset, and it's in a different position than when it started. And this graphic is showing the difference in index of refraction, where the exit point might be different because the different indexes would cause the light to bend more or less and exit at a different point. Refraction angle. The angle that the light wave hits the surface also matters. If the light hits the material exactly perpendicular to the surface normal, then it will pass through and the light doesn't bend at all. Right, so in this example here, where the light goes straight through this glass that it's directly facing, that's because the light wave is entering the surface straight on and not hitting one side of the wave and turning it. The more extreme the angle, the more extreme the refraction. This is why light appears most warped at the edges of curved surfaces. That is where the angles are the most extreme. We all sort of know this intuitively when we're looking at things in everyday life, but it's good to take a closer look, right? This also happens with reflective objects like this chrome sphere. So things in the middle seem, pretty normal, and then when you get to the edges of that sphere, because the angles are so extreme, it starts to really warp the entire world. And the same thing would happen if you had a glass sphere. So in the middle, it looks pretty normal, and by the edges, you're distorting it quite a bit. In this glass on the table, we can see through this middle part where there's not too much curvature, where you can even make out, part of the coffee cup that's behind it. But then towards the edges, it starts to just get really warped, and it's actually the environment that we're seeing just distorted quite a bit, and especially on this stem of the glass, where you can sort of make out a coffee cup even here, but then everything else is just so extreme in the amount of distortion that's involved. And this image of the three glasses is showing that, depending on if you're looking at the glass slightly to the left or slightly to the right, it is distorting that background that we're seeing at slightly different angles, and they're showing up as completely different, even with a slight change of direction. This is exactly what causes lens distortion to be more extreme at the edges of the frame versus the center of the frame. We've all seen a fisheye lens before, and we know that In the middle, it starts to look pretty normal, and by the end, all these buildings and trees are changing direction so much and curving so much, and that's why when you have an image like this that you're trying to undistort, it's mostly the edges of the frame that are receiving that undistortion, and the middle is relatively left alone. So let's stack these topics together a little bit. Combining the more extreme distortion on the edge with the color separation is why we get chromatic aberration more on the edges of the frame as well. The more extreme the angle, the more extreme the refraction, and the more extreme the separation of the colors. Now let's talk about caustics. Light refracting through complex shaped objects changes direction and concentrates those lights towards certain areas more than others, and those create caustics. And I thought this was an amazing illustration on the right side, showing that the different angles of the light entering, they're causing them to focus on different points, and that's the bright points that we're seeing when we're seeing light passing through a glass of water or something. Complex shapes create complex caustics, and moving surfaces like water create dynamic and organic moving caustic patterns. So it's the same effect, it's just that the surface of the water is moving, and that's what we're getting here. And finally, what is translucency? Transmissive materials have a roughness or glossiness setting that works in a very similar way that it does on specular highlights or a metallic shader. Increasing the transmission roughness causes the light rays traveling through to scatter or diffuse or blur together. Think of frosted glass or plastics in real life. This effect of blurring or scattering the transmitted light is called translucency. Again, this is a setting that you can apply to the material, so the transmission roughness as it goes up, it starts to look more like frosted glass and becomes more translucent. Let's do a quick recap of all that. So transparency, you can see through to the background as if the material or the object is not visible or ignored, as if it's not even there. Transmission, light is allowed to pass through the surface and material onto the other side. Refraction, light changes direction as it passes through the material or the surface. And translucency, light passes through the material and gets scattered or blurred. What I still had a problem with when I was doing this video is not quite understanding, why this transmission pass, was only showing up with the beauty inside of it, and why the same thing was happening in the indirect specular. And I thought to myself, these two passes must be related in some way for them to be doing, the same thing. And while I was doing my thinking or philosophizing or pounding my head into a wall about why these two passes are doing this, I started to come back to the same point. And that point is that in both this reflection and what we're seeing through the glass, the result of what we're seeing is not actually the object. So when we look at this mirror object, we're not actually seeing the mirror itself. We're seeing a virtual image of this glass full of balloons here. And we're not actually looking at the surface of this mirror. It's like we're looking past it into another part of the scene, right? And the same thing is occurring when we're looking through this glass, and that it's distorting the table and the environment and everything around it, is that we're not actually looking at the object, the glass. We're looking at the world distorted through it. Before you shut the video off and cast me off as crazy, let me try to explain what I mean by what I'm saying. So when we're looking at fully reflective or refractive objects, we're actually seeing a distorted representation of our surroundings. We could consider these virtual images or even virtual worlds. This effect can be very obvious in concave and convex reflections. When we're looking at curved mirrors, it is very obvious that the objects that we're looking at is redirected and distorted view of the surroundings environment. So here are some mirrors that are either curved towards us or curved away from us. And if you need an immediate example of this, just go to your kitchen and pick up a spoon. And on the inside of the spoon is going to be the concave side where the whole world is flipped upside down. And on the back side or the outside of the spoon, it's going to be the convex side where you're a little bit ballooned out. The shape of the object that is doing the reflecting is actually quite important. So this is a convex mirror, or a metal, you can consider it. So the light is not entering the surface or anything, it's just bouncing directly off. And when it's curved away from the light source, for example, here, the light is bouncing and spreading out in the different directions. And that's represented here by these light beams that are hitting this mirror and spreading out, right? The opposite of that would be a concave reflection or concave mirror or metal, where the light is bouncing off and the middle of it seems to be pushing inwards or going away from the light source. And that's causing the light to bounce off and then focus back inwards. And at a certain point, it reaches a critical point here, the focus point, in which the image then reverses itself. And so you can see that in this example of the light hitting this curved metallic surface, and then it bounces inward and all of the light rays cross, which is exactly what's making the inside of that spoon flip the environment around when you're looking at it. The same exact effect is happening on refractions through glass, for example. So we've all picked up a magnifying glass and watched things get bigger, and we've all picked up a lens before and watched the world get smaller or look like a mini world inside of the lens, right? A concave refraction, or a concave lens or glass, that causes the light to pass through, and while it's passing through, due to the bending, it starts to spread out. So that causes the light beams to hit the surfaces and exit and spread out, making the initial image look bigger on the other side, and that's what a magnifying glass is doing. The opposite of that is a convex refraction, or convex lens or glass, and that is causing the light to bend inwards when it is passing through the glass, and once again all the light focuses on a certain point and then reverses itself. This is exactly what's happening in the internals of a camera lens, for example. And so you can see the light passing through and then bending inwards, hitting the focus point, and then spreading out again, and the image is reversed. The reversal of those light rays are what is making the buildings look upside down in this glass sphere. So I'll put all these graphics on the screen right now, and you can start to see the pattern or the relationship between them. So in reflections, the light either bounces off and converges or comes together, or the light bounces off and spreads apart. And in refractions, it either passes through and spreads apart, or passes through and converges and then flips. You start to realize that reflections and refractions are doing the exact same thing to the light, except that in reflections, the light is bouncing off the object, and in refraction, the light is passing through the object. And that is the only major difference. But in both of these cases, the end result of what we're looking at is light rays that have been distorted. So we're not really seeing the actual object, we're seeing the result of the light rays that are going in all kinds of different directions, right? This giant structure here is called Cloud Gate in Chicago, also known as the Bean. And it's just a giant curved metal thing that looks like a beam. It's in Millennial Park in Chicago. If you ever get a chance to go there, I really recommend it. But just take a look at it for a second. And what are we actually looking at when we're seeing this thing? I mean, we're not seeing the object itself. We're seeing like the entire world completely bent and forming a shape that we recognize because we're so used to seeing these distortions on a daily basis as this kind of bean shape, right? Aside from some dirt or scratches or something, we're just seeing the distorted environment. So in a lot of ways, that scene from The Matrix where he says, you know, don't try to see the spoon, it's impossible because there is no spoon. It's kind of true in this situation. There is no spoon. There's just the distorted environment. And so I'm going one step further in saying there is no glass either. So when you look through a glass of water, what are we actually seeing? Like, does the glass have any properties? We're seeing right through it, right? The only thing that we're actually witnessing is the complete distortion of our environment around us. And we can see that with this bird going up and down, right? It's just mind-boggling what we're looking at. We're looking at a shape of distortion that we identify as the glass shape. And of course, there's some specular reflections on the outside of the glass, but if you take that away, I mean, we're just seeing a completely warped and distorted surroundings. The next time you reach for a glass of water on the table, I want you to think how you even know that glass of water is there if it doesn't have any color or anything. You're essentially reaching towards what you perceive as the 3D location of the source of distortion of your entire environment. Now that we've seen the relationship between reflections and refractions and how one's just bouncing off and the other one is passing through, we could start to look at where this effect would belong in the render passes. And so basically in other videos in the CG compositing series, we went over extensively the difference between diffuse and spec, and then there was emission, which is basically just when you see a light. If you consider the diffuse pass all light interaction with the material and the object, so it's describing the actual object, the properties of the object, the color, and so forth, and the specular as all surface reflections, you know, the light's hitting right at the surface level and bouncing off. we have no place to put the refraction effect. What happens when the light passes through it? We can't put it in the specular, and so therefore we need a new category. And this new category is transmission, or refraction in some cases, and that is all pass-through refractions. So instead of light hitting the surface and bouncing off, the light is hitting the object and passing through, and we can't put it in diffuse, and we can't put it in specular, so we have a new category of transmission. And transmission is a lot closer to specular, so it's not describing the object like the diffuse pass is. It is redirecting the light, right? So it is the close cousin of the specular pass, and it's acting very much in the same way. In fact, the transmission pass can be separated into direct and indirect and transmission albedo, just like the specular can be divided into direct and indirect and specular albedo. So you might say to yourself, well, I need like an equally as big category here. So, it's the same as a specular. I'll give it its own space, and it'll be divided into direct transmission and indirect transmission, and I'll play with both of those features. However, when we look at the direct transmission and the indirect transmission, we noticed a pattern, which is the indirect transmission seems to have the majority of everything in it, and the direct transmission either has nothing or very little. So it has some of this hair here, but the scale, for example, in the shot doesn't really show up. It's just some little pixels are being lit up, but not really that useful, to be honest. We can look again at this classroom render, and if we look at the direct specular, we're seeing direct reflections of the light sources, and then the indirect specular is the light bouncing off the scene and bouncing off the surface. But then when you look at direct transmission, it's completely empty. So I'm cranking up the values here, and we don't really see anything in it. And we have to look at the indirect transmission to even to see everything, and that seems to be where everything is living. It's all living in the indirect transmission. Let's take a quick look at how the direct and the specular passes were broken out as far as direct, indirect, and albedo. So we have over here diffuse with light interacting with the material, and we have direct with it, which is the first bounce of light, so light bouncing off the object then to the camera. Indirect, which is the second bounce and beyond. It could be 100 bounces, could be 4 bounces, so second and up, right? Which everything else in the scene. And then we have albedo, which is describing the color or the texture map of the said object. Then we have the specular category, which is all light reflecting off the surface of the object. And once again, the direct is the first bounce, the light hits the surface and bounces off. The indirect is the second bounce and beyond, just like the diffuse was. And the albedo is more of a filter, or like how much are we seeing the specular. It's a multiplier. And then we have the transmission pass, which is acting exactly like the specular pass, except it's all the light that it's passing through the material. And we also have the direct, which is the first time we see the light passing through the material, the indirect, which is the second pass through and beyond that, and then the albedo, which is also the filter, or how much, or the multiplier of that transmission. If you have the transmission pass set up in your AOV rebuild tree, which you really always should, because we do want to catch the cases where the light is passing through the material, right? So we do want to see that. But more often, the transmission pass just ends up being rendered black, completely black. And that is just because it is more common to see specular reflections. Like almost every object in the world has a specular reflection. And metallic objects are nothing but specular reflections, right? They don't even have really a diffuse. But only certain objects have a transmission. So only certain objects allow light to pass through them, like glass and water, gases and stuff. So those aren't as common, and we usually see more black renders of transmission, and only when we see an object with the transmission property, it shows up in that pass. So here we have a representation of that, where we have just kind of a normal material, like a bowl of fruit, that will have a diffuse pass and a specular pass, right? And those are reaching the camera. And then we have metallic and reflective materials, and that is basically just specular pass. It's all going to show up in the specular pass. It's all reflective. And then we have transmissive or refractive materials, and that has the light passing through it, and all that light that's passing through, in this case, will end up in that transmission or refraction pass. But those materials also allow light to reflect off or bounce off, and those still end up in the specular pass. So just pick up any glass object in your house and you'll see that it is allowing the light to pass through it, and also on the surface level it is reflecting the light in the scene. We could consider that every time light is hitting some sort of reflective or metallic surface, that it is undergoing some sort of reflection event. So the light is not making it from the object to the camera, but it's changing direction via a reflection event. And then all that information is then stored in the reflection pass or the indirect specular pass. And the same thing is going on here when the light is redirected through a refraction event or like a glass shader or something. So as soon as it's redirected, it's considered a refraction or transmission event. And then that information is then stored into the indirect refraction or indirect transmission pass. We could say that both of these events are creating a virtual image because the light that is reflected is shifted in position, or it's bent. And so the thing that we're seeing is not really there, it's somewhere else in the scene, right? So that is why these events are important, and they're also the second bounce. So first the light is hitting the bowl of fruit, and then it's going through the glass and redirecting, and that's kind of considered another bounce. And so everything ends up in the indirect pass. Going a little bit deeper on this point, we're noticing that the number of light path events are putting the results into different passes. For example, if the light is directly seen by the camera, it is in the emission pass. If the light bounces once off of a metallic or mirror object, if it just has one bounce, then it goes into the direct specular. If the light bounces off an object and then bounces off a mirror, it has two or more bounces and goes in the indirect specular, or you can consider it the light bouncing off two mirrors. So again, anything with two bounces or more, they all end up in the indirect specular pass. So following the same logic, the light passing through only one side, so it's only transmitting one time, that will end up in the direct transmission. Whereas if a light passes through two or more sides, so it transmits through two sides or more, it will end up in the indirect transmission. To kind of prove this theory of why everything is ending up in the indirect transmission, I set up the scene with the classroom in Blender where I have just one plane, just one-sided plane here as a glass object, and I put a cube glass object on this side, and we're going to look at the results of those. You can see that it's offsetting the scene, it's having an index of refraction, and things are a little bit distorted. We can see that in both cubes there is a light source being shown through it, but only on the single-sided cube do we end up seeing the light source. We have a little bit of artifacting here, but we're missing the light that we should see. If we're thinking about lights passing through, they should end up in the direct pass. That is true when it's only one side. And we can see on the indirect, we can see that the light is missing from the single-sided, but everything shows up in the indirect when it comes to the cube that was glass. So this one-sided glass is proving that it's following the same logic as the diracular specular, for example, where the light is bouncing off the surface, and then all those go into the direct specular, while everything else goes into the indirect specular. The problem doesn't come with how the pass is being made. The problem comes with we almost never refract through only one side of glass. If you've ever modeled any glass object in 3D before, you have been taught that you should never just do a plane of glass. Every piece of glass should have a thickness. That means that it has two sides at the bare minimum. And this is trying to mimic exactly what happens in real life, right? Every object has an entrance point and an exit point. It's not just one infinitely small plane of glass, right? So everything has a thickness. And that's the reason why we're supposed to model the glass in that way. But that also means that basically by default, if we have thick glass in our scene with some sort of thickness, that almost everything is going to end up in the indirect transmission. The glass in 3D having a thickness basically eliminates this one-sided pass-through, so you almost never see the direct transmission, or very, very rarely. This is why most of the glass refractions are ending up in this indirect transmission pass. In this scene, we do get some direct transmission in the hair, and maybe the hair is really thin, or it's on cards or something like that, and so this is a unique case perhaps. But that is explaining that all these glass have some sort of thickness to them, and they're all showing up in the indirect. Because this is most often the case, you often don't need this huge transmission section dividing up everything the same that you do in the specular. Even though they're acting in the same way, it is much less common to see useful things in the direct transmission. This is why in many CG renders you won't even see the separation of direct and indirect transmission. It'll all just be showing up in one pass called refraction or one pass called transmission. And if you do have the passes separated, I would probably recommend just saving some space and doing the little combine of the direct and indirect and the multiplication of the albedo if you have it, and just kind of putting it all to the side here so that you can adjust it all at once. It's much more common to see the transmission only showing up in one pass like this, which is combining the direct and indirect together, because it's really not too useful to separate them. One of the reasons why the renderer chooses not to break up this indirect specular or indirect transmission pass might have to do with the fact that both have a roughness setting, and when you increase the roughness setting, everything becomes blurred together and therefore not as useful to break apart because it's all just blended into one. If you go back to the render of the glass objects in the classroom, because everything is in the indirect pass of the transmission, you might be worried that, oh, maybe I need to adjust the specular of these objects here because it's very clear and there's no roughness and we can make out what everything is. That need goes away very quickly if you start increasing the roughness of the transmission, because everything starts to get blended together and you can't see the specular highlights from the diffuse and where they begin and end. So they start becoming far less important to separate out. And that could be one of the reasons why it is deciding to chuck everything into that indirect pass. Let's recap what we've learned so far. Transmission means light passes through the surface or material. Refraction means light redirects, bends, changes direction, however you want to phrase that. The CG pass could be named either transmission or refraction, but they're often referring to the same phenomenon here. Light passing through and changing directions. Specular and transmission passes are both very similar in that they are capturing light that is redirecting and showing a virtual image of the distorted surroundings. Emission is the light source. Diffuse describes the object itself, the material properties of that object. Specular events captures light bouncing off the object's surface. Transmission events capture light passing through an object's surface. And these all get separated into their own categories. Both specular and transmission have the following in common. A direct pass that shows the first reflection bounce off or the first transmission pass through of a light. An indirect pass showing all subsequent bounces or pass-throughs. And an albedo filter that you could consider a mask. Transmissive surfaces like glass are often modeled with two sides and given a thickness. Therefore, the light usually passes through two or more sides and ends up in the indirect pass, and the direct transmission pass shows up as empty. So it's often rendered as just an overall combined transmission pass for convenience. I feel like this render example helped me a lot in thinking about how closely related the specular and transmission pass were, where we have here a fully reflective ball that is reflecting the scene. We can see when we look at the ball, we're fully seeing the whole environment. And then we just rendered the sphere again with a fully refractive shader. And from there you can see, again, it is showing the environment now through the glass ball instead of bouncing off the front of the glass ball, right? But in both situations, it is not showing us something that is actually the ball itself, but the whole environment. And that helped me kind of realize that instead of a speck that was bouncing off, it was a speck that was going through kind of thing. This conceptualization is also supported in the fact that the ball is 100% reflective. In fact, I think there is no diffuse component to this reflective sphere. And if we compare it to the transmission pass, we can see that they're both fully showing us what's in the scene. It's just that some of the other objects have specular components, which are shown in the specular pass, but none of the other objects are see-through or have light passing through, so that's why it is isolating the item like that. But if you just look at the sphere itself, maybe it'll be more clear just how similar they are. The next thing we need to think about is where to put the transmission pass, because it's just as important as the diffuse and specular. It's its own thing. So the question would be like where to assemble this in our AOV rebuild. And I had to think about it, and for me, it kind of makes sense to put this transmission pass between the diffuse and specular, and I'll try to explain why. If you look at this diffuse, we're missing kind of some objects. and the transmission at least gives you some of those. And especially in this glass example, this is showing us everything through the glass. And just from a layering point of view, if we look at the specular pass, we see that some of the reflections are of the glass surface. And so just as like a layering example, those reflections from the glass would go on top of the transmission. Yeah, so when I switch the transmission to be at the end, for example, which is totally a viable way to do it. You can do it like this if you have it like this in your setup. But for me, it kind of is strange to see this object as black and then add things that are behind the specular highlights. So for me, I'd probably want to build up from diffuse and then transmission and then specular, even though, of course, the transmission pass does have like specular highlights inside of it. I think it just makes a little bit more logical sense. We can see in this V-Ray example, I set it up the same way. So you have everything that is diffuse, and there's some objects that are not showing up, like this table, which is a glass top table. Then the refraction would go on top of that. And then the specular comes last, which is adding some reflections that are on top of that surface. So kind of layering-wise makes a little bit more sense. I've rearranged some of the setups that I've already gone over in this video to reflect this placement of the transmission. So between the diffuse and spec, in this classroom, for example, you would have all the diffuse of the classroom, and then, for example, the hallway and the clock would show up. And on top of that, you'd have specular, and at the very end, you would have emission, which would be the lights at the very last step. Same thing for this junk shop. We would have the diffuse pass, then the transmission, which would give us some more details in the scene. Then the specular on top, adding the highlights. Emission, which would be these kind of light sources here. And this render came with volumes, which I guess is the smoke from this little robot guy. I mean, if I were rendering this in production or anything, I would render volumes on the side. So if you do happen to have volumes in your render and you need to add it back, of course, just start adding whatever it is, the pass that you are rendering like off to the side at the end, I think is probably fine. I'd like to draw attention to the fact that the transmission section is not as big or spread out as the diffuse and specular, and that is basically because the indirect and direct are not that important, since most of the transmission shows up in the indirect. So in the case of Blender, it was able to render direct, indirect, and the albedo pass, but usually that's not the case. It just comes in as one render pass. So in either case, basically it doesn't need as much space because most of your color corrections are going to be done on top of everything. So I didn't spread them out in the same way that I did the diffuse and specular, and tried to keep it nice and slim so it doesn't, take up unnecessary space. The same with the emission, like it's the same idea. It's only one render pass. There's not much. You're either controlling how much emission or where it shows up, so there's not too much to do there, and you don't need the section to be as big. I did return to the fruit bowl render examples. I decided to build in where the pass would go if there was something in the refraction or transmission pass. So I redid the realistic proposals with this addition for the Redshift and Arnold and Octane rebuild proposals. So you'll see that whatever the pass was called, and I did render the passes, they're just empty, right? So that's kind of why I didn't show them on the previous video, because we were going to get to it in this video, and maybe it would have just been a little bit confusing to show black renders. Depending on what renderer you're using, it will call them either refractions or transmission. They're all empty in this case, but I tried to respect the naming convention of the renderer. So whenever the pass said transmission, I named it transmission. And whenever it named it refraction, I named it refraction. So I will provide these new setups so your renders will work if you are rendering refractions or transmissions. Okay, so we've talked about what refraction or transmission is, why it's occurring, what it's trying to replicate in real life, and why it all ends up in one pass. But still the question is, what can we do as compositors when these passes come in looking like the beauty in either their transmission refraction pass or the specular indirect reflection pass? So what can you do further when you get the note of adjust the highlights or change the colors of the balloons? Well, the sad truth is that you can't do that much, so you're going to have to bust out your toolbox of hue correct tools or all your tricks to, adjust the different highlights and colors, just like you would to a beauty render, right, when you couldn't separate it. So as a compositor, we are pretty limited to what we can do once the passes end up like this. we're going to need to ask for help from the lighting artist. And there are some tricks that you can do as a lighting artist to help further divide these types of passes. So we're not stuck completely with these types of renders. That's not really our problem to solve as compositors, but more of a render problem to solve for the lighters. But there is at least one trick I can show you with regards to dealing with planar reflections. And the most typical type of planar reflection you're going to see as a compositor probably is going to be a ground plane reflection pass like this one. And we went over this problem before, but basically the indirect specular pass contains all the information for the reflection, so you can't go and adjust the AOVs of your reflection. So in the case where it's a ground plane render or any mirror surface, this render has a flat plane mirror surface, for example. For those types of renders, there is something that we can try to do. Usually lighters do not render the reflection with the actual object itself all in one render, but rather they'll render just the object by itself with its own alpha channel and the reflection separate, which will still end up in the indirect specular reflections pass as just like one beauty that you'll then comp the actual object on top of like this. So we're going to try to get a better version of this reflection that'll be more useful for us in comp. Let's very quickly go over what planar mirrors again. You can see in all these images taken in real life, they happen to be on the ground plane here, but it's basically just a single plane in three-dimensional space reflecting the entire world, like upside down, basically. It's the mirror dimension, if you want to call it that. This doesn't just have to be ground plane mirrors. It could be a mirror at any angle as long as it's a flat plane. And you can see that the mirror is reflecting other objects in the scene, and it's almost as if the camera is right here facing this direction and shooting this object from like behind the mirror. So that's kind of the idea that we're going to use here. So in order to get this specific effect we're going for, we need to flip the camera along the normal of the mirror plane, and that will produce a virtual camera for you to render the mirrored virtual image from the right perspective. So in this case, the pivot point, imagine this is the ground plane, it is just flipping it in the Y. So we're going to do negative Y, and that will make the camera flip in world space to go under the ground facing up. And you can see if you flip it, you'll align the perspective and get the image that you're looking for. I brought in the geometry for the armor mech into Nuke, and you can see I have a 3D view of it right here with the camera. And if you set up a ground plane like this in Nuke, you can set up a reflection node and a ray render. That will give you something like this, where it is actually rendering the reflection on the ground plane. And right now I don't have any textures or anything, so I'm just using a checkerboard. But this is matching the angle of our render, so let's just use this as a visualization because it's easier to do at the moment. This specific example is only going to be useful in one case where the ground plane is at the origin, so it's flat along the origin of the ground. In other words, it's a card spread along the ground plane of the 3D scene and hasn't been moved or rotated or anything like that. So in this particular case, that was our mech machine that was sitting on the origin. You can see that the legs of the mech are, barely passing through the ground. So it is sitting on the actual ground plane in the 3D scene. So this is an example that I'm going to show you in Nuke, but should be applied in any 3D scene when you render the object. So this can be applied in Blender, Cinema 4D, Maya, whatever. It's just a basic practice, but it's just easier for me at this moment to show you in Nuke. So you could, of course, flip the geometry, but usually it's easier just to flip the camera than like all of the objects in the scene. So we're just going to flip this camera. If you make a new axis, it's sitting at the origin of 3D space, and pay attention to these arrows that are showing the orientation of the axis. So it's just a default axis, and all we're going to do is basically scale the world in Y. So we're going to flip the world in Y. So if I just go -1, you'll see that the arrow has changed position and it's flipped everything. I think a more basic visualization of this might be just this cube sitting on top of the ground here. And if I do a transform geo, by default it won't do anything, but if I plug the axis into this invert, it will just flip it around in 3D space. So now it's sitting under the ground plane, completely inverted. And that's what's happening to our camera here. And in Nuke, in order to apply transformations to a camera, you need to plug the axis input of a camera into an axis that has a transformation. So when we plug that in, we can see that it flipped the camera around in the world. And maybe if I just go very slowly, you can see what it's doing. So if I just go along, you'll see that it's really just scaling negative until it hits 0, and then it starts going the complete opposite direction until it reaches its destination point at -1, which would be just completely scaling the world upside down in this case. And if we go to render our scene now with the flipped camera, if we see the output of that, we're going to get this result here. And this is exactly aligning with our armor mech reflection only pass. So we recreated, at least in the position, the armor reflection pass and how it is oriented. So just by flipping the world, we've recreated the reflection. Of course, we cannot render this in Nuke with all the lighting and AOVs and everything. So we'll need to do this in our 3D application, or have the lighter do it, or we could even export this Nuke camera for the lighter to render the scene with. So applying that new camera flip or inversion or mirroring technique, I just went back to Blender and did the same to the camera and rendered this result. And this is not a reflection, it is the actual mech viewed from the upside down camera. And if we do something like that, you'll see that we end up with all of our AOVs the way that we would see it in a normal beauty render. So here's all of our specular highlights, and we are now a very happy compositor because we can go and adjust all of our passes. And in the end, you could have one AOV rebuild for the actual object and one AOV rebuild for the reflections, and copy some, for example, color corrections to both of them, where if you're adjusting the colors pretty extremely in one, it will be also adjusted in the reflection, which is really what you need when you're going to these extreme levels. But what if your reflection is not on the ground plane and it's not as easy as just flipping the world upside down in Y? And what if it is a reflection just in an arbitrary direction in space like this, where we have it behind our armor mech and showing you from the reverse angle there? So then it becomes a little bit more difficult. You can see from our 3D scene, we have a plane just randomly rotated and facing the mech, which is being rendered by the ray render and giving us this result. So what do we do in this kind of situation? Well, the card in 3D space has an orientation, if you see by this handle here, and the Z handle is showing us the direction of the normal of the card. That you could think of that as which way is the card facing. So from the card's point of view, this would be the direction that is in front of it, right? And this is much easier to do actually in a 3D application, because you can just set your pivot point to the card and then scale, in negative Z or negative Y, whatever the direction that you need to scale the world. It's a little bit harder to do this in Nuke, actually. So without getting into too much of the math behind this, you can do this in Nuke. You just need to have the orientation of the card, which is represented by this handle. So I made a tool called Mirror Dimension. And just like we plugged in an axis to our camera in the previous example, we're going to plug the card into the camera, but the in-between node is going to be this mirror dimension. And basically, in a nutshell, what I'm doing is taking the card's orientation and then flipping the world to the opposite side of that card. So wherever that card is, it's going to flip the camera or the scene into the opposite side of how that is oriented in 3D space. If you want to look inside, I'm basically doing a little bit of matrix math, and the end result is actually an axis. So you can consider this plugging an axis into the camera, but it needs to know where the card is. And if we plug this mirror dimension into the camera, we can see that the camera jumps from one side of the card to the other. And it won't matter which way this card is oriented as long as you plug it into the mirror dimension. If I rotate it, for example, you'll see that camera is following the axis of the card, so flipping exactly to the other side. And that's why I called it the mirror dimension, because you're filming the object from the mirror's perspective. So this is the result from the scanline render of the inverted camera. You can see if I unplug this, it goes back to its default position. So we're filming it from, the point of view of the mirror. And I can test this by doing a wipe between the ray render result and the result from the mirror dimension camera. And you'll see that the reflection is in the same place. And one is an actual reflection, which is coming from the ray render. And the other one is the camera that is repositioned to film from the perspective of the mirror. And the gizmo has no settings, it just has some instructions and has one mirror card input. It's meant to go between the card and the camera here. And you can use an axis, it's the same result. So if you only had an axis, you can also use that. But yeah, if you had a card, I think it's a little bit more visual as to where the camera is going in 3D space. So I'll include this tool in the blog post and probably put it in the Nuke Survival Toolkit and post a link to that GitHub page. And yeah, you can try this out on your own and see if it works for you. So what happens if you just have the render of the object, but your lighting team is now on holiday in Miami, sipping pina coladas on the beach, and there's no way to reach them? What can you do as a compositor to perhaps fake a reflection? And some of these techniques that I just talked about translate over a little bit to how we could fake a reflection as well. Well, if you have the geometry that you can bring into Nuke, you can do, for example, a camera projection using the render and project 3D. You can just project that onto the geometry like this in 3D space. And from there, you have the option to have your reflection card. In this case, I'm just going to use the ground plane and, for example, use a ray render. The result is not going to be perfect because of the way that the projection only sees one side of the object. You're not going to be able to project the underside of it, so the reflection on the ground is seeing like up above and underneath the mech, so you're not going to have that information. But maybe if you just needed something rough as like a placeholder or something that you don't look at too much because it's very subtle and maybe blurry or distorted, this could help you. There is kind of the problem with the ray render where it's going to show you actually the object that is reflecting. I don't think there's a way to turn off the object and only keep the reflection. There's no way to like hide it, I guess, because if you hide the object, it also hides the reflection. So we could do the same mirror invert camera technique to get just the inverted reflection pass. So we could use something like this if we had access to the geometry. Well, what if you don't have geometry and you only have the render pass? Is there anything that we can do as compositors? Well, there is one more trick where if you have the position pass, which I'm not going to get too much into, but basically it's telling you the location of each pixel in 3D space. So each one of the RGBs is a coordinate, so it will put the pixel color in that coordinate in 3D space. So if we use a position to points node and plug that into the position pass, we'll get something like this, which is just the points plotted in 3D space. And you can see, it's only going to work from the angle of the camera and everything else will be not visible. But these are just little colored points that are in 3D space. You can see if I zoom in really close, you can see each individual pixel or point in 3D space. It's always good if you have the actual geometry just to double check if they are lining up in the correct position. In this case, you can see that it is sitting happily on top of the geometry. So it is doing the right points in the right 3D position. And once you have your little point cloud representation of the 3D object, you could either flip the entire scene with a transform geo, for example, and you get this result. So it's just flipped it in world space, or you can just flip the camera like we have been doing. And then you'll receive basically that point cloud rendered from the camera's mirror perspective. And you can see there's still lots of holes in it and everything, but it'll give you a decent enough result. And maybe this result here is good enough for your needs as a reflection. It's certainly, I think, better than trying to take this thing and scale it in Y, for example, because the legs won't line up. And, that's always a classic nightmare. So this will at least give your connection points much more accurate than what you would originally get if you just tried to do it in 2D. Sometimes reflections are very subtle and all it needs is just a little bit of horizontal blur. I'm just using an eye blur with a little ramp here. As you can see, I'm starting to get some interesting results that could pass for a type of reflection in comp. And I'm not using any 3D geometry here. I'm just using passes that came with the render and that you will typically find in production, and then doing a little 3D setup to get that reflection. So hopefully that gives you some ideas of how you could generate your own reflection if you have these passes. And I'm just going to show you that the projection geo technique works with the mirror dimension camera. So we'll get this result from the projected geo technique. And the point cloud technique also works with the mirror dimension camera. You're just viewing the point cloud from another direction. the more extreme that the reflection angle is compared to your render angle. For example, we can't see what's behind the mech from just a point cloud from our angle, but you'll get something which perhaps you will find useful for a reflection, especially if you are going to blur it or something. So it's better than nothing, and it might give you something that'll save your ass as a compositor someday. That is the limit to what I can show you from the compositing side. I have no more tricks up my sleeve for how to fix some of those annoying passes in transmission or in indirect specular. So that's pretty much all you can do from the comp side. However, there is more that you can do from the lighting side. I'll just show you an example of what you can do using something called light path expressions. So in a typical render like this, we would have an empty diffuse pass and everything would show up in the indirect specular. But using light path expressions, we can end up getting a diffuse pass that has the reflected information of the diffuse of other parts of the scene in it, and also other subsurface scattering and separating out the specular as well. And similarly, where this sphere would normally just show up in the transmission pass, using light path expressions, we can get the diffuse pass with the refracted diffuse pass all in one, and the subsurface scattering and the specular broken up as well. So this is a really big deal, and on certain shots, like if you have something reflected in a helmet or something, and it's close up in the screen, you might need a solution like this where you can have the diffuse pass as it is viewed from the refraction or reflection angle. And that is the power of these light path expressions. But I'm not a lighter, and I would feel uncomfortable trying to show you how to do this in the lighting world. So I called up my friend and colleague Julius Ihle, who is the head of lighting and LookDev at Trickster. And in fact, he has his own blog where he shows many of the techniques, such as how to handle reflections and how to handle some of the light path expressions. So I'm going to show you the conversation and screen sharing that I had with Julius, that he can go through some of these things more in depth and show you some solutions that you can do in the lighting side when it comes to these light path expressions and the power of them. I do encourage you to go check out Julius's blog at julius-ihle.de, and there is just so much information for lighters out there, and he's really passionate about sharing and teaching as well. So it's just a great conversation, and I hope you guys take something from it.
Most of the time, it just boils down to diffuse and specular, and both diffuse and specular can be either reflected or transmitted. Actually, what you can think of, like I mentioned, you have two main shading properties that you oftentimes have when light is interacting with the surface. Basically, you have diffuse and you have specular, and both of these can be either reflected or refracted. And refracted you can also just as well call transmitted. For these terms, for example, what you can think of is if you have, for example, diffuse and you reflect it, what is output usually in the at the end as an AOV, or what the shader is outputting at the end, is what you usually have as a diffuse AOV or diffuse response. If you have a diffuse transmission, it's what the shader is usually outputting as subsurface scattering, or what is called subsurface scattering. If you have the same thing, reflection and transmission, you can have for specular as well. So if you have a specular reflection, that's usually what you end up with as specular, as you usually have it. And a specular transmission is usually output as or called refraction, for example. Maybe it's a good thing to show actually in a sort of a live session. I know this is the maximum of my artistic ability at the moment, but basically I have like a refractive sphere. And if you, a lot of the renderers usually by default, if you have a transmission or refraction pass or however it's going to be called, you're going to see something like this. And the obvious issue that you're going to end up with is that if you wanted to, I don't know, for example, grade the color of the torus here, you would need to, it's going to be very hard because the refracted one is obviously you would need to affect as well, but it's not part of the diffuse. If I look at the diffuse, it's empty inside everything that's behind the glass sphere, and it's in the transmission, but it's going to be obscured by tons of other stuff. And the way that I think this always used to be a problem. There used to be like hacky ways to get around this in older style renderman, but what they did come up with a few years ago, I suppose. I'm not entirely sure from when this originated, but there's a concept for creating AOVs specifically in path tracers that is called light path expressions. And the cool thing about this is that because path tracers, the way that they work is really simple, right? You start from the camera, you shoot rays out, and you basically tracing them. They interact with a surface. Some of it is going to be, for example, diffuse. Some of it is going to be a specular, and then they're going to continue bouncing around until you hit the ray depth limit. And the way that they work is quite simple, but also leans into the fact that because everything is just a mathematical equation, the renderer keeps track of, okay, what is actually a continuation of the diffuse bounds? What is a continuation of the specular bounds? And so on and so forth. And you can actually follow the light paths with those light path expressions. Now, this is definitely the same in RenderMan, in Cycles, in Arnold, and I think pretty much every renderer has this supported now. And it's a little bit technical sometimes because those expressions can potentially get quite complicated, but the way you can think about it is you start with, you basically tell the renderer, okay, which path am I supposed to follow? So you start, for example, with, you always start usually from the camera. Then you say, for example, everything that is a diffuse surface interaction, and then whatever ends up at the light. So you go from camera to diffuse to light. And here I can do that. I have an empty AOV. It's just called test. And usually the renderers, it's like, you have to Google it a little bit where exactly you enter them and so on. But here you can write down a light path expression. So if I write the CDL inside here, what I'll get from it is, so to speak, all direct diffuse reflections. And that is exactly what you're gonna get here in return. The thing is, what you can see here is that this torus that is also part of this AOV now, because as I mentioned before, torus, or sorry, subsurface scattering is its diffuse transmission effect. So you could narrow this down if you only wanted actual diffuse. You can say, instead of just D, you can say RD, which is a reflective diffuse event. And then you only get, in this case, this is exactly the same as a diffuse direct AOV. And you could, and what you can now do is you can say, okay, if I'm thinking about the path of light that it's meant to follow, is that first I go through the sphere, through the front side, which is a transmissive specular event. Then I go out of the back side, which is another transmissive specular event. And then I hit the diffuse. And I want to have this included. So I want either, all starting from the camera, I want reflective diffuse. basically exactly what I have here into the light, or I want to start from the camera and then have a transmissive specular event and maybe some more, then again reflective diffuse, and then ending up at the light again. And the nice thing is that the way that these light path expressions are set up is that they work as regular expressions. I'm not an expert in this and mostly just Google around, but you have a couple of tokens that you can use to specify, hey, I want this event to be 1 time, 2 time, X amount of time, 1 or more times, 0 or more times, and things like this. And the way that you could do it in this case is that you say, I want to start from a camera, then transmissive specular event, and I want to have that transmissive specular event either 0 or more times. 0 times, 1 time, 2 times, 3 times, whatever many times. And if I do this, I get exactly that result. So now I have the usual reflective diffuse, and I'm also checking if there's any previous refraction events. And that way I get exactly all of the diffuse component inside here as well.
Yes, what you're showing here is what most people would assume would show up in the diffuse pass. But you're saying there's a limitation because it's going through a transmissive event or a refraction event, and then it gets like put into another box, and it just shows you later.
Exactly. The thing is, if you think about it, it would otherwise be quite tricky to get consistency across, because at the end of the day, you kind of want to have the same output for all of the AOVs. So if I, for example, had a mirror, which I think I do, and it's just reflecting stuff, what you get in specular AOV, or like specifically in, if this was specular indirect, which is only the second bounce. Maybe I can quickly add that here as well. So this is just all the stuff reflecting. Yeah. Now, usually you're not interested in splitting that up because the most of the specular things that you have, are kind of rough speculars, and it would be unnecessary to split it up into individual components. However, you might want to do that when you are when you have something like a mirror. And the reason why oftentimes this is needed for refraction is due to the fact that a lot of times when you have refractions, it's clear refractions. So you want to, you exactly see what is behind it, and you usually want to have full control over it. If I go back to the example of the sphere I had, if that sphere was more rough, for example, then you wouldn't really, you just have a blob like this, and then it's then like, yeah, exactly. So it's mostly due to the nature of refractive objects that they are oftentimes very clear, and you see exactly what objects are behind.
And from what I was reading online, it's a very similar reasoning to why the refraction does that, because you could also have a scattered refraction too, which would be all this kind of blurriness, and then it would be pointless to try to divide everything into diffuse and spec and everything, because it would be one muddy image.
Yeah, if you have something like this, it's like there's no point really in splitting it up into different AOVs. So it's only for specific cases. Light path expressions, you could, because sometimes you maybe want to do the same thing with a reflective sphere, for example. And the cool thing is that you can actually do that as well. So if you remember from what we had before, it's like, okay, all the transmissive specular events, maybe I want all the reflective specular events. And then now I basically have a diffuse only reflecting in the sphere here. If I look at the specular indirect from before, it has all the beauty, but now I basically have, for example, my diffuse, but included also in the reflections here. And same thing I could do, for example, for subsurface scattering afterwards.
Mhm.
So I could you have very fine-grained control over what you want to isolate, and in theory, you can end up with like a gazillion different outputs.
But
Oftentimes, you don't need it. But
to clarify, what you just did with the light path expression, you invented a new AOV. You're not
exactly.
you're not altering the fact that diffuse is only going to show you normal diffuse things. So you're basically reassembling a new diffuse pass with some special sauce mixed in.
Exactly.
So that's why you could do it, but you're not getting it for free. There's no
Exactly.
one check box that you clicking in it.
I should mention it. It's a very good point. I almost forgot to do this, to mention it. By what you can also do, and this is a little bit of a particular thing to Arnold, and I believe some other renderers have it as well. I'm not sure about cycles, but you also have a way of, if we go back to our refractive sphere, if we go back to the refractive sphere, so now it's refracting again. Arnold, specifically in the standard surface, has a checkbox, and as far as I know, that is in the newer version even enabled by default, and that will basically do exactly what I just previously did manually, but automatically for all the AOVs. So now if I go into diffuse, I have diffuse and my transmitted diffuse as well. If I go into specular, I have specular and my transmitted specular.
So this is the refracted specular and the refracted diffuse, and that's possibly checked on. Where can people find that? It's
in the Arnold standard surface shader under the transmission tab. I think under advanced, there's a transmit AOVs checkbox that will basically do it as a checkbox for you, because like you said, it's a very common thing to do. So they added it as a default.
That's amazing.
Well. Yep.
That's really really cool and informative. I didn't even know that existed. So maybe you said it's kind of new.
I think it's been there since a while, but I think it's only recently. Before it was off by default, I think, to maintain backwards compatibility. But I think I just checked it today, and I realized that it was on by default. So I think in the newer versions, it's on by default already. So
they're doing us favors. Good.
Yes, exactly.
Yeah,
I completely agree. It's usually something that you want to have happen by default anyway. So it makes sense.
I think
to have it on.
It's more confusing if you don't know what's going on. It's really confusing. Like, why I can see through this glass to the object. Why can't I just refract? Just refract the scene and the diffuse. But
yeah,
turns out that it can. But maybe in some older renders or some other renderers that it's not doing that yet.
Exactly.
From what I've gathered from what you've talked about, we have the diffuse and the specular. And if the diffuse and the specular goes from the object to the camera, we see diffuse and specular.
Mm-hmm.
But if there's something in the middle that is either a reflection or a transmission or refraction, that basically gets put into another box. So the diffuse gets reflected. Okay, now it's a different thing. And the specular gets transmitted. Now it's a different thing. And what you were saying is that you still have access to those things theoretically. So you can remove the reflection event and remove the transmission or the refraction event and go straight back to the original diffuse and the original specular.
Exactly.
But by default, those events are putting, like, as soon as it hits a reflective surface, as soon as it hits a refractive surface, it then becomes its own category.
Yeah, exactly. What I think is a really good resource for that as well is the Arnold help. If you just Google light path expressions, I think it's even the first thing that comes up, and they have a lot of they basically have an overview over, description of the AOV, the name that is available in the UI of most DCCs for Arnold, how it's going to be called, and the corresponding expression for it. And this, I think, is quite a nice learning ground together with the original documentation, because this really goes into detail of like how it works. And the Arnold documentation, I think, is quite a nice overview of some practical examples. Like if you are looking at, for example, let's take one like diffuse. Diffuse direct is literally from the camera. You hit the diffuse surface and you go directly to the light. If you want the diffuse indirect, you do the same thing. You go from the camera to a diffuse surface, and then any other event after that until it hits a light or an emissive object is stored inside of that. And that's kind of makes it maybe also a little bit more clearer to see that anything for all of the indirect ones, anything that happens after the primary event is just, you can think of as a beauty. So this is, in this case, any diffuse specular volume or emissive events after that.
It has them all. It has them all as letters in there. Diffuse spec volume.
Exactly. There's a the documentation has a good overview over what the individual events are. They differ a little bit from renderer to renderer, but there's also some like
and such.
Exactly. But there's some visual examples here as well, which I think is a nice learning resource as well.
This is amazing.
Some good examples.
Really, I didn't come across this. It's super good.
You can do so much. You can do so much stuff with it. You could, I don't know, for example, if you, in the case of reflections, for example, if I go back to this test scene, we wanted to, for example, have reflective events and then, I don't know, only use events after that are not even including any of the any specular afterwards. You can do all of this stuff. It is quite powerful what you can do in the first place.
Yeah, it's like writing down exactly what you
exactly
want
what path you want to go.
It's in equation form.
Yeah, some things are a little bit more tricky to get out, but you have still so much more flexibility with this, which is can be handy in a lot of situations.
Do this light solution. So if you have a problem where you have a mirror on the ground and the comper is asking for, hey, I need AOVs, or I need what such and such for this reflection, how would you go about solving that problem in a realistic setting?
So the problem with that is a little bit that with light path expressions, you can do quite a lot of things. The problem is that it is a little bit limited because you're only tracing the actual path of the light, or the path that the light is taking, and doing all the shader calculations and things like this. But it becomes a little bit tricky if you wanted to get additional tag passes, like position, PREF, that kind of thing out of it, because it's not an inherent part of what the renderer is tracing. Like there's no need to trace the reflected PREF, for example. If you think about it, like, yeah, okay, you can have like mirror-like reflections, but a lot of the times, even if it's like wet ground, it's still like distorted and maybe a little bit rough at least.
Yeah.
And in those kind of situations, if you have, for example, a position pass reflected in there and the values are blurry, you're not really getting the actual position that you are after. So one thing that I did was a couple of years ago, maybe I can show a demo in a second as well, was to set something up exactly like with where you can take everything that you want from a exact mirror-like reflection, and then have all the tweaking possibilities in comp. Because the issue is a little bit that if you have a ground, or if you have like a flat plane, mirroring the scene or the camera is perfectly valid approach.
Yeah.
And it just makes sense, because you
Yeah.
get everything that you need for free. But it becomes a little bit tricky if you have something where it's not exactly a mirror.
Or even if you have a wall and a ground, because then suddenly you have two planes, and then
yeah, exactly. And then you need to have two renders just for reflection.
I was basically purely thinking of like, yeah, I have a mirror, or yeah, this is just for comp for the ground on like a puddle or something. Okay, cool. We can just render the mirror dimension. But yeah, as soon as it's curved, or as soon as they have multiple angles, then it's totally out the window, and you'll need to resort to what you're referring to, I think. So this is sort of a solution for when the planar mirror dimension flips. Sorry, when it doesn't work. So it fails you, and now you need to resort to some sorcery.
Exactly. So I mean, this is Katana, but it doesn't really, it's a universal approach that can be used, because you can write. Basically, what I did is I wrote a shader specifically for this problem, and similar to light path expressions, there's a common shading language that most modern renderers can use, which is called Open Shading Language, or OSL for short. And you can basically write, it's like scripting a shader, so to speak, that usually, for the most part, depending on what you're doing, is universally working for all the renderers. And you can do stuff that is either tricky to do with nodes or not really possible out of the box. And something that I did in this case is you can basically, in all renderers, you can create your standard AOVs, like specular indirect, for example, that is just a reflection of the object. But you can also write custom data into a channel. One thing that I could do is I could just pipe in, create an additional AOV that I'm just going to call reflection A. And I can type any sort of color or any sort of output directly in it. And the shader that I wrote is basically a simple reflection without any like roughness or parameters to it. So it's literally just a mirror-like reflection. But what you can do is you can read data from the original input. So you can either give it like a solid color if you want to create, for example, an alpha for it, or you can pass it a component to trace. So, for example, you can have the reflected world position. So that would change accordingly if I would move the object as well. And or things like UVs or normals and things like this. And all of these can be reflected. And because this doesn't incorporate any roughness, you can use it in comp right out of the box, which is in that sort of way.
And this will work on not just a planar surface, right? This will work on a sphere or something like that.
If I had a sphere in the background as well, and it would just reflect exactly, it would do an actual reflection, but just in a non-blurry.
Okay. So what you were saying is, if they're using this open shading language, if they have access to this, they could theoretically recreate this for whatever renderer they're.
Exactly. So I also have a shameless plug. I have this on my blog as well.
Show us the blog if you have it up. Highly recommend people go.
I'm not very good at updating it, but whenever I have a little bit of downtime, I make some personal.
So this is playing with open shading language, number 5.
Yes, exactly. So it's exactly that example that I just went over, and you can download it here as well from
GitHub.
GitHub.
Amazing.
So it's trace AOVs, and Depends a little bit on the renderer again, where you need to put those files. But once you have them, so in this case, it's trace AOVs, and if you have it in the correct location for your renderer to pick up, then you should have it available as a shading node.
And is this pre-canned AOVs, like you wrote them, or they just give a name of an AOV and then it reflects it?
It depends a little bit. So this is referring to globals that are available within OSL itself, and these are usually it can be user data that is attached to geometry. For example, if you, I don't know, in the production scenario, you get a mesh from effects that has data mapped to individual points. You could reflect that. You could have custom data like PREF, for example. I'm not sure.
What about a texture pass where I have some veins of a character with some skin details?
You can pipe all of that in as well.
Cool.
In this case, if we go back to the sphere example, you can see now I basically get the reflection of that as well. Now, in this case, the sphere is also in return reflecting the ground.
Yeah.
But this is, you can, there's things that are called trace sets in renderers where you can say, okay, I want the reflection only of this one and exclude this one, and you can go quite crazy with it.
Yeah. But if the sphere was the only thing in the scene, it would just be reflecting the horse in this case.
Exactly. And the good thing is that you can basically set up your scene however you want, and you always get, like the actual raw data of all of these passes out.
What have you done here?
The cool thing is, so it's basically exactly the same thing that I just demoed, and I just have an alpha for the reflection. I have position for the reflection, and this one is a little bit of a particular thing that I also have that on the blog, but it's basically giving you a black and white ramp of the distance of how far the reflection has traveled. If you think about reflection on the ground, so if I make this reflection more rough, you can see that the top part of the torus that is reflected here gets way more blurry, and maybe an easier thing to see is with this
more distance has allowed it to spread out a bit more.
Exactly. The further it is away from a visual point of view, the further it is away, the more blurry the reflection gets. And as a form of example, I can obviously now properly grade the reflection as well if I wanted to, because I have an alpha for it. So I can do things like lifting the black point and stuff like this very, very easily. And also I can use this distance as a mask to blur it more the further it gets away, right?
So instead of relying just on the render to try to match it, you can kind of fine tune it a little bit. Right?
Exactly. And you could do things like, because everything is rendered, right? So if I don't think I have it here. No, I don't have it in this render, but if you had like a position pass for the ground, right?
Yeah.
You could map some noise onto it and then use this
Roughness.
to break up the render a little bit. And you have like so much control in comp that you can do all of these sorts of things.
It's better to start with this unblurred smooth result, like the pure reflection, and then just sort of do your comp tricks. Sometimes it's fairly easy to do these kind of like defocusing based off of this reflection distance. This would totally work as a Z depth pass that you could pump into a Z blur, I think, or a Z defocus.
Yeah.
So yeah, this is amazing, and it's giving you the reflection distance, not the actual distance of the object.
Exactly. It's not the distance from the camera, but the distance of the reflection, or the object is away from the plane at each point on the surface.
Yeah.
If I had this moved further away from the plane, it would get brighter. And also the thing of like having an alpha for it, you can see, you can kind of, if you have an alpha, obviously you can achieve this blocking effect that you have in the original reflection. And I think I kind of like this approach, because oftentimes it wouldn't really make sense to try and match all of that in lighting, because even in a simple scenario like this, you have so much little detail on the table, which is way easier to control in comp. I want to break it up a little bit more here. I want to break it up a little bit more there. And you have all of this control directly in comp, because you have all of the AOVs. And
yeah, I mean, this is a great example of when things start to enter the comp world of being just not only just easier to do, but just like probably giving you better results of more accurate. Because as you said, I would make a clean plate of the ground so it looked like everything was where the shadow of the cup is, and I would make the whole ground look like that, and then I would use the alpha to reveal that surface basically.
That's perfect. Exactly.
Yeah,
make it look great.
There's a big lesson in that. You don't always just plus your reflections, because you have to realize that it's actually occluding the light behind it. So you have to see the actual character.
I think a good way to think about it is if you have CG on CG, usually you plus it, but as soon as you combine it with the real world, obviously you have to try and imitate what's happening there.
So there is a solution out there for the hopeless situation where a good old mirror dimension planar reflection is not going to do it for you, and you can get some AOVs still out of a complex reflection. Thank you so much for your taking the time to go over some of the stuff with us, because it's really, really helpful.
Yeah, I'm hoping it's clearing some things up, because I understand also there's not that much resources online on these kind of things.
Yeah, it's difficult to even know what to look for some of these answers. But yeah, so you recommend people definitely checking out open shading language and light path expressions. Is that OSL and LPE?
Yes, exactly. Yeah. It's even if you are not a 3D artist yourself, I think light path expressions, just like trying to get the gist of it, can be quite useful, because even if you don't set it up yourself, you can, at least it gives you a talking ground of when you're talking with a CG guy that you might be working with. It's like, hey, in this specific scenario, I want this particular, I don't know, reflection, for example. Can you maybe help me out with that?
Yeah, to specify, to be able to communicate better, like what you're looking for. Yeah,
exactly.
It's amazing. This is really cool. Really, really cool. Thanks, Julius, for
no worries,
for all your help on this subject. I want to say a huge thank you to Julius for coming on and sharing his knowledge with us, and for providing some of these renders that you see where it's demonstrating these light path expressions. Thanks for tuning in, and I'm glad you made it this far if you did, and hope to see you in the next one.